A real power grid has thousands of buses, the points where lines and machines meet. How does a computer solve a network that large? All at once, it packs the entire grid into one matrix. That matrix is the Ybus, the bus admittance matrix. Every power flow study and every short circuit study begins by building it. So let's build the Ybus step by step. Here's the idea behind it. Every component we have built so far, the generator, the transformer, the line, became an impedance. Impedance is the opposition to current. Now, we turn that around and use admittance instead. Admittance is just 1 divided by impedance. It is the ease of current flow. So, a line with low impedance has high admittance. The whole network is buses, joined by these admittances. For one component, Ohm's law says the current is the voltage times the admittance. And here's the beautiful part. The same law holds for the entire network at once. We write it as one matrix equation. The injected current at every bus equals the Ybus times the voltage at every bus. One equation holds the whole grid. So, how do we fill the table? There are 2 simple rules. Here is a small network, 3 buses, joined by lines. The table has 1 row and 1 column for each bus. First, the diagonal. Each diagonal entry belongs to 1 bus. To find it, we add up every admittance connected to that bus. This is its self-admittance. So for bus 1, we sum the admittances of the 2 lines that touch it. Second, the off-diagonal. Each off-diagonal entry links 2 buses. To find it, we take the admittance of the line directly between them. Then we make it negative. And if 2 buses have no line between them, that entry is simply 0. That is the whole method. Sum the admittances at a bus for the diagonal. Negate the line between 2 buses for the off-diagonal. Let's build a full one. 3 buses in a triangle. The line between bus 1 and bus 2 has an admittance of 4. Between 1 and 3, it is 5. Between 2 and 3, it is 2. Now, the diagonals. Bus 1 touches the 4 and the 5, so its entry is 9. Bus 2 touches the 4 and the 2, so it is 6. Bus 3 touches the 5 and the 2, so it is 7. Now, the off-diagonals. Between 1 and 2, we negate the 4, giving -4. Between 1 and 3, -5. Between 2 and 3, -2. And the matrix is symmetric, so each pair matches across the diagonal. There it is, the full Ybus, straight from the diagram. One honest note. Real line admittances are complex numbers, but the method is exactly the same. So we have the matrix, but what is it really for? Let's look closer. Each row of the equation is a real physical law. Take the first row. On screen, it becomes a single equation. It says the current entering bus 1 depends on its own voltage and on the voltages of the buses it connects to. That is just Kirchhoff's current law at bus 1. The current in equals the current out. So each row is an equation. It is the whole network written in one line. Now, the payoff. Usually we know the currents flowing in from generators and loads, and we want the voltages at every bus. So we solve the system. In matrix form, we invert the Ybus. This inverse has its own name, the Ybus, the impedance matrix. It gives every bus voltage from the currents. A computer does this for thousands of buses at once, and this is exactly how a fault study finds the fault current at any bus. One honest note. In a power flow study, we know the power, not the current. So the computer solves it step by step, not in one shot, but it always begins from the same Ybus. So, the Ybus. It is one matrix that holds the whole network. Admittance is 1 over impedance, the ease of current flow. The diagonal for each bus is the sum of the admittances that touch it. The off-diagonal between 2 buses is the negative of the line between them. And each row of the matrix is one network equation. So, the currents equal the Ybus times the voltages. Solve that system, and we get the voltage at every bus. That is the heart of power flow and of short circuit studies. Next time we solve it properly, the power flow problem. Subscribe, and see you in the next one.